Hi, AP Stat students. We're going to dive in and look at our next unit, which is sampling distributions. Um, and we'll just kind of go through this whole thing one step at a time, and we'll get through the whole unit hopefully by the end of the week and through a few videos. So the first thing we're going to do is, I guess, just go through the Khan Academy assignments. And the first thing we're going to do is just review what we know about the normal distribution and normal CDF and our calculators. So here we go. We get a question, and let me zoom in on the calculator, and let me zoom in on this assignment. Hopefully that shows up well in the video. Let's see here. Just a little bit more zoomed in. Awesome. Okay, so we're going to review just how the normal distribution works and what's going on here. So we want to find the score of a randomly selected tester from this group of SAT college-bound seniors, and then we want to find the odds that this one student we selected had a score less than 1200. So let's first draw this out, there we go, and figure out what's going on here. So we've got some sort of distribution that's normally distributed. Doesn't have to be a perfect normal distribution curve, and the average score was 1497. That's a very high score, and the standard deviation is 322. So that essentially just gives us some scale. Specifically, you want to recall the empirical rule, which says, hey, if you're plus or minus 1 standard deviation away, you're covering 68% of the data, and if you are 2 standard deviations away, you're covering 95% of the data, and if you're 3 standard deviations away, you're covering 99.7% of the data. So that's what we have going on there. And just to say, you know, this is kind of living in my head the whole entire time, this kind of spacing, so that when I look at 322 as the standard deviation, and I look at 1497 and 1200, I can kind of quickly do some mental math and say, well, that's about 1500, that's about 1200, and that means these two are about 300 away, and my standard deviation is about 300 away. So that just gives me some basic idea that this 1200 is somewhere around here, and I want the odds that I'm getting less than that. So it's usually just, I don't know, a good idea to draw some kind of distribution and get some sense of where you are on that distribution. Where's the mean? Where's the mean? Where's your value? But crucially, how far is that value from the middle, since we have a standard deviation to compare that distance? So yes, it's 300 away, but 300 is actually just one standard deviation, which is not that rare or unusual. So how would we then do this in the calculator? Well, we would go to second distribution, normal CDF, and since this goes left forever, the lower bound is some huge negative number. That doesn't make sense. I mean, obviously we can't score that on an SAT. The upper bound is that 1200 because that's where I stop. That's as high as I can go because that was the cutoff value. The mean 1497, standard deviation 322, paste, and there's my answer, and to 2 decimal places that would be 0.18. The other thing to do is just to say, remember that you can do this just using tables and not using normal CDF, but what you're going to have to do is calculate the z-score. So first, yay, we got the question right. But let's see how we can do this without the normal CDF, or how do we do this without a calculator? Well, we take the value we're interested in, we compare it to the mean, 1497, and we then divide that by 322. And again, you can see that's why I was putting my placement at about the 1 standard deviation mark. I kind of talked you through what a z-score was verbally just by saying, hey, there's our mean, there's our value, but it should only be about this far away because that's about 300, and 300 is about what a standard deviation is worth, and there's the z-score. That's what you're doing in a z-score. You're measuring how many standard deviations are you from the middle, to the left, or to the right. And we want the area to the left of that z-score, so we could take out our z table, and we could find negative 0.92, so negative 0.9, and that's 0, 1, 2. I get 0.1788, which also to 2 places rounds to 0.18. So there we go, 2 different ways of getting the same answer. Maybe we'll look at 1 or 2 more of these questions. And yes, I did only get 1 out of 4 correct because usually what I do is I just scroll through these and find a question I'm interested in starting at. So now we've got a two-sided question. We've got where or what area is between two values. It's not one-sided, so to speak. There's not one cutoff, there are two. All right, well, let's just, again, draw the picture. We'll do it faster this time and then more so rely on normal CDF. So in other words, I just want to remind you that there is a way to do it with the z-scores, but of course we are usually going to just use normal CDF. So 26 is in the middle, 2 is what a standard deviation is worth, and I'm going from 26 to 30. So in other words, I'm going right from 26 2 standard deviations away, because again, 30 is 4 units away from 26, but a standard deviation is worth 2 units, so moving 4 when a standard deviation is worth 2 means I'm 2 standard deviations away, or about right there like I pictured before. So I actually want this area. It's a little interesting. I mean, it doesn't change the complexity of the problem, but it is just interesting to note that, hey, this time the lower bound is just literally in the middle. You know, we don't see that often, but it doesn't change how we approach it. We're still going to go to second distribution, normal CDF. My lower or furthest left I go is the 26. The highest I go is the 30. The mean is 26, and the standard deviation is 2. And I get 0.477 into two places, that would be 0.48. I am just wondering if they do any inverse normal. It doesn't look like it. So here I go skipping around again just to see if I can find maybe an interesting example. Not necessarily. Okay, so I think that really does it for this first assignment. Just be really careful of drawing that picture and getting a sense of what it looks like on the normal distribution. That's really where we need to be comfortable with. Drawing the picture, putting our mean in the middle, trying to, it doesn't have to be perfect, but understand that, yeah, I am about 2 standard deviations away, so I definitely shouldn't put the 30 right here. I also shouldn't put the 30 way over here. It should live somewhere around here because that's about where 2 standard deviations is. Again, maybe just Google what the empirical rule looks like. So that being said, let's dive into the next biggest idea, which is the central limit theorem. And here's, in essence, what the central limit theorem says. The central limit theorem says that if you care about measuring means or averages, then as long as you sample 30 or more individuals, then the expectation of what you get is going to be normally distributed in its shape. So I am going to kind of supply some definitions and things to write down, and we'll explain that more clearly. But again, the essence is if you sample more than 30, then no matter what your population looks like, and that's kind of what's going on here, they're saying the entire population shows a skew right distribution. But if I sample more than 30, this what I would expect to get from this as an average would actually be normally distributed. And so I'm going to show you what that looks like here using this kind of online tool. So we don't really need that right now. Here we go. So what I have here is a very heavily skewed right distribution, and the mean is 4.51. And it says, hey, I could choose sample sizes of, let's do 5. That's actually what the Khan Academy problem had. It said we're going to take random samples of 5 and calculate their mean. And so if I do that, okay, I want samples of 5. Let me generate one sample, and you can see I now have one dot just sitting right here. The question is, what is this one dot? And this one dot is what I get when I, again, choose 5 random individuals from this population, 5 values from these 877 distinct values, and I take those 5 values and calculate their average. That's why there's only one dot here. So I'm not taking 5 individuals and plotting their 5 values. I'm taking 5 individuals, collecting their average, and just putting that in the distribution once. So far I've done that with one sample, and I could keep clicking this button. Now I have 2 samples. You can see I'm getting wildly different results, and that's not unusual because, after all, I only took a sample of 5 people. When you sample really small, or when you do something only a few amount of times, you can get some pretty unusual or uncommon results. And let's see what happens as we keep on doing this. Eventually, sampling one sample of 5 at a time and calculating the average takes really long. So I'm going to start doing generate samples 100 at a time. And you can see what we start to do is we start to get a distribution. Maybe I'll sample 1,000 at a time. And the key here is that because I'm sampling 5 individuals at a time, what I want you to notice is as I am plotting the averages of my 5 individuals, the shape of this distribution, the shape of the distribution of my averages is also skewed right. And so that's the big idea of the central limit theorem. If you sample a small amount, then the average you get is going to have some sort of distribution to it. And you start sketching the distribution of, again, what you expect to get when you take an average. And it turns out that when you sample less than 30, then that shape of what you expect to get from an average happens to match the population. So that first question, well, I'm taking samples of 5, aka a small sample, from a skew right distribution, and we just saw what happens. We would expect that what we're going to get, our sampling distribution of the average, is also going to be skewed to the right. A small sample is going to match its population characteristics. All right, so once again, I've got a small sample, less than 30, but it also says, we can just kind of look at this. This looks pretty normally distributed. It's got a bell shape to it. It kind of looks like those distributions I was drawing earlier. So then, because I'm sampling less than 30, I'm going to match my population characteristics. It also says it follows the normal distribution. So because I sampled small, I matched my population, but the good news is this time my population was normal. Great. All right, up next, now we're sampling 45 individuals, and let's see here. They actually don't tell me what my distribution looks like. But guess what? When I sample 45, this is what the central limit theorem says. If you don't even know what your population shape looks like, it turns out that sampling more than 30 and measuring that average, or measuring what you would expect to get on average, is going to be normally distributed. And let's show you that even with this same example. So let's reset. I still have a heavily skewed right distribution, but let's do what that last problem said, and let's take samples of 45. Again, if I just go one sample at a time, what I'm doing is I'm taking 45 individuals every time I click this dot. I'm taking 45 values from this distribution, and without repeating, and I'm calculating its average, and I'm plotting the average I got from those 45 individuals. And as I start to do this, again, how many have I sampled at this point? 15 samples of 45, that's a lot of individuals, but I keep on going, keep on going, keep on going. One other note to say is as I take a sample of 45 once, again, I'm not repeating any of those 45 values. After I'm taking that sample of 45, just to say, we are then putting them back into the main. So for the next time I take a sample, there is the 877 in total. Anyways, let's speed this up and start generating a lot of samples. And we get a very interesting thing start to happen. Even though this was skew right, take a look at what's happening. The true average is 4.51 for this population. Now we haven't got it exact, but what I do have is I have a very symmetrical, some would say almost normal shaped distribution that is almost, because we are randomly sampling, we're never going to be exact likely, but we're getting very close to the true population average. And maybe if I even take a few more samples of 1,000, you can see now I'm getting even closer. I'm getting closer to that 4.51. If I do it a few more times, maybe I'll get closer, maybe I'll get farther. But this is this really, really interesting property that we've discovered, that even though our population individually has a skewed right shape, what we expect to get from an average when we sample a large amount of individuals is a normal distribution. So again, what we're showing here is the distribution of averages from a skewed right population. The distribution of averages from a skewed right population, as long as I'm sampling more than 30, is approximately normal. So that's why the question is correct. Even though we don't know the shape of this population, even though they never said what it looked like, I know that I'm going to get a normal distribution for what I expect to get from a sample because I sampled more than 30 at a time.